previous video I was not quite clear and there were a lot of confusion. I hope I'll be able to clarify this time. I'm going to write the code again. So first I'll define the phantom, not region. Yeah, so what I'm trying to do is, in my previous video on FRED, coding FRED stands for fast particle therapy dose evaluator, and it runs on GPU, which makes it faster than CPU powered Monte Carlo engines. And that is the flagship thing about FRED, being fast. And now I am going to show you how to run a simple single beamlet, proton beamlet, in a water phantom and to evaluate the dose. So first I'll define my phantom. I'll name it as phantom. I always like to give, okay. Phantom origin, I'll keep it as 0, 0, 0. So this origin is global, in context with the global coordinate where this origin will be. And then when pivot will come, I'll tell you. So this is my forward vector, in which direction the beam will go. Will it go in the x direction? Will it go in the z direction? Will it go in y direction? So by writing it as like this, the third coordinate implies z direction. So it will go in the z direction from negative to positive side. But what if I write like this? How will my beam go? In that case, it will go diagonally from, in 3D, if you have a cube, from leftmost corner on the front to the uppermost corner to the bottom of the to the top of the cube, diagonally. I hope I'm making sense. Anyway, let's keep it simple. I have the forward vector, now I have the up vector, and this I say that y direction is my up vector. The reason to define this vector is to make sure when we rotate the beam later on in the simulation, when the simulation gets complex and we are defining beamlets and the geometry is quite complex, then we have to take care of the how we are rotating the beam, the proton beam. So in that case, we have to define which side is up. And once we know which side is up and the forward vector, the perpendicular to them will be our left or right vector, the x1, the vector in the x direction. So by defining these two vectors, we can find out, I mean, the code automatically knows about the third vector. My water cube is 10 centimeter cube in each direction. And here comes the pivot, which is quite confusing. So what pivot says is, you have the cube, and at what point, what should be the isocenter at which the beam will be focused. So when I say 0.5, 0.5, and let's say I say it again 0.5, that means my at global coordinate, the entire cube, the center of the cube sits at 0, 0, 0. I hope you get the point. Now if I do this as 0, now in the z coordinate, my cube starts at z equal to 0. That means still in xy plane, it will be, the beam will be going through the center of xy plane, but this plane will start from z equal to 0. I think I have an image for this from, again, it's not my image, it's from FRED. They have done a good job with the documentation, and I hope I can I cannot drag and drop and it will go away. No. Okay, wait. So I click this. Yeah. So right now my phantom is sitting like this. When I say 0 comma 0 comma 0, that means the 3D the cube entirely sits like this. It goes from, for example, here it goes from, because here let's say the cube is of 20 centimeter cube, it goes from minus 20 centimeter to 20 plus 20 centimeter in z direction, assuming this is minus 20 centimeter in y direction, plus 22 y direction, and then again out of the screen and into the screen. You get the idea. So that's how that is where our beam will enter. Now this voxel, you can define it. Do you want to keep the voxel as 1 millimeter of size, each voxel of like 1 millimeter cube, or you can decrease it? How do you do that? Because voxel size is given in millimeters, so 10 centimeter divided by 100 millimeter is 1 voxel. I mean, the voxel unit of voxel is 1. If I do it here as 200, then 100, that is 10 centimeter, 100 millimeter divided by 200 millimeters will give us the exact voxel size of 0.5 millimeter cube. So let's keep it as 1. Okay, we have our voxel, and of course we are simulating it as water phantom. Yeah, that's our region. That's done. Now I will define my beam. So to define my beam, first I have to give it a ID, which is field ID 1, and there has to be origin of this this field beam, because this, as I was thinking, this field beam is not a single source from which the beam will emerge. In this simulation we have to define the field box from which the beam will emerge, because in that matrix, the field box, the proton, we have to define the initial divergence or convergence, how the proton will spread when it comes out. I mean the beam, not protons only. Yeah, of course the protons, how the protons will spread, the divergence, the radius of the protons. So all those has to be defined initially, and that cannot be defined at a single point by just giving a point and then defining like a lot of protons coming through out of it. We have to define a matrix. That matrix will take care of the spread, angular spread, the beam spread, the divergence or convergence, the emittance, all of those things. So that's why we define a beam matrix of certain length, breadth, and depth. And let's keep it at minus 40, because our cube starts at z equal to 100. Let's say the screen is, for example, and this part is 0. I will keep my beam where the point from where the beam will emerge, somewhere here at minus 40. I hope you get the idea. Yeah, of course I have to define the matrix, the field box. We can't, yeah, I was thinking why not just give a point and let the proton come out of it, but it's not efficient to do that way, or it would be not realistic case to just give out some protons of certain energies and them not undergoing any spread or convergence or divergence. Yeah, I hope you get the idea. So this pivot now I have the field box from where the proton will emerge, and this pivot says that the beam emerges at the center at the center. That one beam emerges from the center of xy plane, which is 20% inside the beam box. And again, I think I showed you the picture. I'll show it to you again. Again, this is from, okay, let me show it with the website. So this is our field. Sorry for my voice. So this is the field, and this is the field box, and here they have, for example, they have kept the origin at minus 55, z equal to minus 55, and when they say pivot equal to 0 0.5 comma 0 0.5, they're keeping at the center in the x and y plane. And what does this 0.2 or 20% mean? That means this example is for different case. For this case, 0.2 means 20% inside this plane. For example, my the field box starts at minus 40. So at minus 40, the 20% of minus 40 would be how much? 8. So minus 40 uh, plus, I mean minus, it goes inside, like 20% from the inside. So it's minus 40 minus 8. So it would be somewhere at minus 48. So you get the beam comes out from this location, and then it undergoes the beam spread, and yeah, the realistic case that a proton beam would go because of the presence of beam magnets, convergence and divergence. Now we have those field ID, the beam. Now we will define our pencil beam. Again, the ID is 1, field ID is also 1. These are just syntax that FRED uses, and also you can find this example at their on their website. Yeah, the particle that we are going to simulate is protons. Let's do with 100 MeV. The energy full width half maxima would be, let's say, 5 MeV. That means that is the realistic case. In realistic case, we don't never get exact monoenergetic proton beams. Of course, there will be emittance, because when the protons come out of the accelerator, the source, they come out as eclipse, as a not circular but as an eclipse, which if it diverges if it diverges yeah if the divergence is in one axis, it converges in the another axis. That's one of the properties of a beam. And now I am going to define the twist parameter for certain beam size. So if we have certain beam size, we can find out the uh, the emittance, the twist parameters, by this equation, which I'm going to show it right now. Oh, no, not again. Yeah, it is from this website. And twist parameters, so sigma square, this is uh, how what's the how the beam, the standard deviation, I would say, of the beam. Like if you have, how does it deviate from the center, like the mean, from mean energy, from the mean beam, that is given by this this emittance, which is in the shape of eclipse. Of course, it's an area. And then you have the alpha and beta, which are the twist parameters. Alpha tells us about whether the beam is converging or diverging. If it's negative, it's converging. If it's positive, it's diverging. And when it's zero, it's neither converging, neither diverging. And beta is the beam width, the beam radius. I hope I got this right. So when you put emittance equal to zero, you make the divergence and the deviation equal to zero. That means the pencil beam has zero spot size. It's hypothetically, it's exactly what pencil beam should be, with no spot size. Okay, let's move on to defining those. Yeah, let's simulate a pencil beam with no spot size. So twist alpha, let's say zero. It's not diverging, not converging. Twist beta. Oh, I'm taking this value from, we can have any value, and the radius, it doesn't matter because it's gonna be um, uh, beam spot zero, beam spot of zero size. I mean, without any spot, because I'll put the value of emittance as zero, which will make the entire beam as pencil beam, just straight beam. And of course, I showed you this emittance reference plane. I hope now you understand, even though I'll show it to you again. PB, that's there. That will do with 1 million particles, and FRED on GPU is quite fast. I promised you to show the plane. So it's the difference, the distance between, it is the distance between the phantom isocenter and the point exactly from where the beam comes out to be. I think it would be interesting what would be the plane distance when there will be a lot of uh, um, lot of beamlets, if they're not originating from the same field width. I think they will take the average distance, and from there they can define the emittance reference plane distance. Anyway, I hope you get the idea of what this plane distance mean. Shall we run it? Let's run it. Where's the terminal? Let me open the terminal. I put emittance equal to 0. Yeah, there is some float. It might throw some float or something error. Let's cd and no, I think it's an example 1. Clear, and I have to save it. FRED. Told you so. Surprisingly, unknown symbols. Maybe we made mistake while writing this. Twist alpha is afla. We'll make it alpha. Oh, can't believe it ran. And yeah, our code ran without any problem. That is, this time the simulation we did was with 100 MeV protons. We have 1 million protons, and it does not have any beam spot. It's a pencil beam. And now I want to see the result, of course. So this saves the file at a particular document, which I have saved it in my code Jupyter notebook, and I'm not going to write the code. I'll just show you what the output looks like, and I hope it works. So every time any FRED code that I run, it goes here and saves it in this file, and they never change the name. It's always dose.mhd. I'm just going to run it. Yeah, I was already doing some work with pencil beam with different energy. So for example, you see I was doing this one with maybe 120 MeV, and now I have 100 MeV. So it is at 102. It should change. For 100 it should be lower than y. Does not exist. Because I have, okay, I have to mount. I hope I can do this fast on the video. My mistake, I was quite confident that this was the right path, but indeed this is not the right path. This one is the right path, and I have to check back with my other experiments as well. And now if I run it, I should get well. Now the pencil beam appears to be a little bit weird. That's my pencil beam entering, and yes, and indeed the Bragg peak is at 74, because for 120 MeV it reaches around 100 millimeters or something. So indeed our code ran perfectly. It appears like this because now it has zoomed in for that small phantom. For, let's say, for 120 MeV, you will see this scale changing. As a result, the beam will appear smaller. Now for this case, it's maybe at 150 MeV, and because 150 MeV has Bragg peak at higher depth, you will see the pencil beam to be smaller because the scale changes. You see the scale changed. I hope that was helpful. Thank you.